And now we're going to do investigation number 2 of lab number 7. Now, all individual forces acting on an object can be traced to an interaction between it and another object. For example, we know that a falling ball is being pulled toward the earth, but that means that the ball has to be exerting a force back on the earth. So as the earth is pulling the ball downward, the ball is pulling the earth upward. So what factors might determine the forces between these objects? And is there a general law that relates these forces? So let's go to page 157, and there's a little diagram there. Prediction 2-1. Suppose you have a tug of war with someone who's the same size and weight as you. You pull as hard as you can, and there's a standoff. One of you might move a little bit in one direction or the other, but mostly you're both at rest. Predict the relative magnitudes of the forces between persons A and person B. Okay? And just place a check next to your prediction. So is A going to pull on B harder? Is B going to pull on A harder? Or is the pull going to be the same between? Now, the next question is going to be, what happens if we have two people, but one of them is much smaller than the other person? Make the same prediction. Is A going to be pulling harder than B? Are they going to be exerting the same force on each other? Or is B going to exert a larger force on A? And then the final prediction here is, suppose that you have a tug of war with someone who is much smaller and lighter than you. Okay? At the time, the person is going to be on a skateboard, the lighter person, and with some effort you'll be able to pull him or her along the floor. So again, here's our question. Is A going to pull on B with a bigger force? Is B going to pull on A with a bigger force? Or is A and B going to have the same force on each other? So now what we're going to do is we're going to go ahead and do the test. So I'm going to put them on my mask here, so if I sound a little garbled, the reason why is because I have to have a volunteer to have a tug of war with. And so Ms. Lyons has been happy to volunteer here, so come on down. We're going to stand right here. So you stand right over here, and now turn around. Face me, face me. Don't worry, no problem there. And here's a force sensor. You're going to hold that one. I'm going to hold this other force sensor. Oh, I forgot I got to record everything. And what we're going to do is we're going to do the tug of war. So go ahead and push the 0 button on the force sensor there. And if you want, you can see on the screen over there, you'll see what the force looks like. We're going to hook a piece of wire in between us. And I'm going to start recording. I'm going to start recording the pulls. And we'll see. So now it's recording. Go ahead and pull. Go ahead and let it go. We'll just take a look at the screen there and you'll see what's going on there. All right, let me go ahead and stop recording. I'll have to take the line fit there. Now take a look at those two graphs. And you can see that the graphs, when I made a pull over to the right, that's the negative, I'm force B. She pulled to the left, or excuse me, to screen right, which is force A. And as you can see, it looks like they fit one on top of each other. It looks like they had the exact same magnitudes, they had the exact same force, and in fact, what I can do to make things look even more interesting is, let me get rid of that display there, but I'll go ahead and show force B on the same graph. And now when you take a look at the two of them together, it looks like a mirror image of each other. So, if you made that prediction, great. If not, well, that's all right. That leads us to question 2-1. How did the two pulls compare to each other? Right? Was one significantly different than the other? I guess you could say they were equal and opposite. But now comes the fun one. What happens if we put her on a skateboard? Yeah, now she's looking at me with some dread here. Okay, here's what I have is I've got this rolling platform. So I'll just put it there. You go ahead. I'll hold it steady. You go ahead and stand on it.
I'll stand?
Yeah, you can stand on it. Just put one foot in front. Just put one foot there, one foot there. All right. How's your balance? You okay? Okay, good. All right. We're going to repeat the pull. So I'm going to zero my force sensor here. She's giggling on this because this seems so silly. This is good.
I don't want to fall.
You won't fall. You won't fall. I promise I will not pull hard. Actually, I won't pull. I want you to pull. All right. I'm going to start recording. So, by the way, you should be making a prediction already. So who's going to pull harder? Who's going to have the bigger force? I'm force B. She's force A. Who's going to have the bigger pull? Let's go ahead and record and start it. All right? You go ahead and pull. Okay. There we go. We're going to stop right there. All right. I've got it right there. You can step off now. There we go. Good. Thank you very much. Okay. What does it look like? It's another mirror image, isn't it? So question 2-2, how did the two pulls compare to each other? Was one significantly different than the other? And how did your observations compare to your predictions? So the comment here is this is a perfect example of Newton's third law. A force is an interaction between two objects. So if I'm pulling on you, you're pulling on me. You can't tell by that graph there who's doing the pulling. But what happened was she was doing the pulling, and yet she still got pulled forward. There was a force. So she was pulling on the wire, but according to Newton's third law, the wire is pulling back on her. Since she's on the wheels, she gets pulled in my direction. Thank you very much. That's all we need. Last thing is we've got two more questions. Question 2-3, are your observations consistent with Newton's third law? And question 2-4, when you pull on an object with the force sensor, does the sensor measure the force that exerts? Or, let's see, when you pull on a object with a force sensor, does the probe measure the force it exerts on the object or the force on the probe by the object? According to Newton's third law, does this distinction have any meaning? Well, honestly, it doesn't have any meaning. The way the force sensor works is generally a pull is related to as a negative force and a push is a positive force. It's really it's measuring what the push or pull on it is. Okay, I'm going to stop at this point and reset it so we can do investigation 3, which is an examination of tension forces. And now we're going to go ahead and pick up on investigation number 3, which is an investigation of another passive force, specifically tension forces. When you pull a rope on a crate, your pull is somehow transmitted to that crate. Tension is the name given to forces transmitted along the stretches of strings, ropes, rubber bands, springs, and wires. And oh, by the way, it doesn't have to be flexible either. Rods and beams can provide tension as well. As a bit of an aside, the opposite of tension is a pulling apart. An opposite of tension is compression, where we push things together. Okay, is the whole force you apply transmitted to the cart? So you're holding one end of the rope and pulling. The cart is on the other end of the rope and you pull. Is that tension going to be the same on both ends of that rope? So this is what we're going to have to try to investigate. So prediction 3-1. If you apply a force to the end of the rope as pictured above on page 161, is the whole force transmitted to the crate, or is the force on the crate smaller or larger than your pull? Prediction 3-2. If the rope is longer, will the force applied be larger, smaller, or the same? And prediction 3, suppose we use instead of a rope, we'll use something elastic like a rubber band. Okay, will the force applied to the crate be larger, smaller, or the same as the rope? So now we're going to test the prediction. This is going to be force number A. This is our crate. This is B, which is the person pulling on the crate. We're going to use a number of different materials to test those two predictions. We'll start off by zeroing our force sensors, and then we're going to place a rubber band between the two sensors. Okay, so there's the rubber band attached between the two sensors. So the question is A going to be pulling harder? Is B going to be pulling harder? Or are they going to have the same force? Which end is going to have the bigger force? Let's go ahead and do the prediction. Let's go ahead and do the run. Oh, I forgot. Let me turn on the legend so you can actually see the forces. And let's go ahead and do the run. Okay. Now I'll go ahead and stop it. And it looks like, when I rescale it, it looks like they're mirror imaged, aren't they? If I use my coordinate tool, you'll be able to see that at every point, the force of A is equal and opposite to the force of B within a range of measurement uncertainty. But you can see the peak 0.87 on one side, 0.82 on the other side, and so on down the line. Why are they different? Because they're off on their sampling times. That's all. But they're mirror imaged, aren't they? Okay, so go ahead and sketch the graph. Sketch the graph on the axis on page 162. Okay. Next, let me move this. Let me move the. Let me reduce that. There. Now you'll be able to see it a little bit easier. Okay. Question 3-1. Based on the readings of the two force probes, when you pull on one end of the rubber band, is the force transmitted down the other end? It looks like it is completely. Question 3-2. As you increase the force applied to the rubber band, what happens to the length of the rubber band? Propose a mechanism based on these observations to explain how a force is transmitted down the rubber band from force probe B to force probe A. And then question 3-3, indicate with arrows on the diagram above the directions of the force exerted by the rubber bands on force probe A and on force probe B. Easy looking on page 163. The force on A must be pulling to the right, and the force on B must be pulling to the left. But what's the mechanism? What's causing them to be pulled in opposite direction? And the answer lies in Newton's third law. Let me go ahead and bring up the whiteboard again and give a quick little discussion. Excuse me. So there's the whiteboard again. So what we'll start off is we have an object here, and we have another object here. Now, let's say instead of connecting it with a rope or a rubber band, let's connect it with a chain link. If I look on the chain link, I'm going to pull on the chain link in this direction with a certain force F. We know that according to Newton's third law, the chain link is pulling in the opposite direction with a force F as well. On the other end, that force, this first force, F1, gets transmitted all the way through, so this end has to get the same force. So this end here has to get the same force. So there must be an opposing force in the opposite direction. It'll work up to the point where it may cause the chain or the link itself to deflect, but the end result is still the same. If I have two objects in contact with each other, one object here, and they're pulling they're bound by some kind of bond, like a chemical bond. If I apply a force, if one is applying a force on two in this direction, then two must apply a force on one in that direction. That's according to Newton's third law. We've seen that already when we did the tug of war. So let's go ahead to the next object. The next object is bound, and so the force from 2 onto 3 is pulling 3 in this direction. The force on 3 from 3 onto 2 is in the opposite direction, and so on down the line. The end result is, if I'm pulling this end in this direction, that force gets transmitted by Newton's second law to this end over here, and it gets equal and opposite. We can look at it, essentially, it's the elasticity of the molecules, it's the bonds of the molecules that are holding it together, transmitting from one segment to the next segment, to the next segment, to the next segment. Okay, what about, now I said that, let's get back to question 3.2. What happens to the rubber band? Of course, it stretches out, but the force is still transmitted. The force on A from A onto B is still transmitted from B onto A. Okay? Now, let's try this. Make loops on both ends of a short piece of string and replace the rubber band, and let's repeat the experiment. Okay, so let me flip it over. We're going to get rid of the rubber band, and we're going to take a short piece of string and tie it on. Let's see if I can loop that on there. No, I can't. Okay, so I'm just going to have to tie it on. Use an old Boy Scout knot. There we go. Tie it on one end, hook it on the other end. Now I'm going to have to zoom out a bit so you can see. Okay. And let's go ahead and, again, zero the force sensor so there's no load. And we'll go ahead and record and see what happens. Looks like a mirror image, doesn't it? Equal and opposite all the way through. Okay, excellent. What happens if I use a longer string? If I use a longer string, is this going to get transmitted? Well, let me reposition the camera because the longer string is just that, significantly longer. So here's one end of the string here. The other end of the string goes all the way out here. I'm going to hook up like that. All right. Again, we're going to zero the force sensors. And let's go ahead and start recording and see what it looks like. And again, it's transmitted undiminished. The force from A onto B is equal to the force from B onto A. The tension force itself is transmitted all the way from one end to the other. Question 3-4. Based on the readings of the two force probes, when you pull on one end of the string, is the force transmitted undiminished down to the other end? And the answer is yes, it is. Question 3-5, did the string stretch? It may have, but not anything that we could see. Can you propose a mechanism for the transmission of the force along the string? Again, it's the same elasticity like I mentioned before. Each segment of string is pulling on the next segment, which is pulling on the next segment, which is pulling on the next segment. But by Newton's third law, there's a force in the opposite direction because remember, forces are interactions between two objects. For every push, there must be, for every thing pulling, that object is being pulled as well. And now let's get to the last one with using a wire. I have a stiff piece of wire here, and let's see if this works. So, in the first case, we had elasticity of the rubber band seem to transmit it. Now, because the string itself is not elastic, it still seems to transmit. Now we've got a stiff wire, which is not elastic at all. So we'll hook it up to the force sensors, zero the force sensors with no load on it. There we go. We got it hooked up. Let's go ahead and start recording. And we see the force again is transmitted undiminished. The force on A to B is equal and opposite the force from B to A. Okay. So based on the readings of the two force probes, when you pull on one end of the wire, did the force transmit undiminished down to the other end? Did you observe any stretch? Do you think the wire may have stretched a little, even though you might not have been able to see it? And the answer is yes, the wire does stretch a little. We can't see it. There's going to be some deformation, but it's going to be down on the molecular level, down on the atomic level. Now we got one more question. What happens if we change the direction? So, in prediction 3-4, what happens when a string is hung around a pulley? Is the tension force still transmitted fully from one end of the string to the other? So I'm going to pause the recording at this point, so I can reset and we can set up a pulley. Okay, and now I've got it reset. We're going to go ahead and see what happens when we apply the tension over a pulley that we have here. So, activity 3-2, attach a force probe securely to the cart, which we have here. We've got it all set up. Next, we're going to take a look at the graph. There's A and B. Remember, A is pulling in the positive direction. B is pulling in the negative direction. We're going to zero the force sensors with no load. And then we're going to put the string on, like so, hanging it in place. And I'm going to hold this in place, and I'm going to pull with the other force sensor, and let's see what happens. So we zero that, we pull with the force sensor, and there we go. You see? We see that the forces are equal and opposite. What I'm trying to get at, very straightforward. The pulley does not add or subtract from the force. What the pulley does is it redirects the direction of the tension force. But as you can see, the tension force on this end is equal to the tension force on this end. Equal and opposite, I should say, because they're in opposite direction. Question 3-7. Based on your observations of the readings of the two force probes, was the pull you exerted on force probe B transmitted undiminished to force probe A, even though it went through a right angle bend? And how does this compare to your prediction? So I'm going to try, well actually I've got to get this published here, and we don't necessarily need it for the homework. So that's lab number 7 in a nutshell. We'll do the discussions on Wednesday, October 7th. So if you're looking at this after we do the discussion, it should help clear it up what you see. Otherwise, good luck on the upcoming test, and I will see you in class.